Very good. And the point about Soergel bimodules is a little bit that they are very nice. And they are completely explicitly given, so they are fairly elementary in their construction. But on the other hand, they have deep connections to Lie theory and geometry and have very rich internal structure. So we try to understand those Soergel bimodules, and which is a little bit disappointing is that I can't really tell you the history of Soergel bimodules. It takes us too far away from the seminar topic itself. But I rather want to think of want to have you think about Soergel bimodules as a black box. Well, not as a black box, but the history and the original construction of Soergel bimodules and the connections as a black box, and we'll kind of study them in the vacuum. So I kind of need to assume that you believe me that what the seminar is about is interesting, not just in its own right. So I hope at the end of the seminar you will agree that those guys are interesting in their own rights, but also in the connection to other parts of mathematics. I would slightly cheat so the first 3 talks will be about combinatorics of Coxeter groups. So I will start right away in a second. And yeah, you can kind of take those as the shadows of Soergel bimodules. So all the nice combinatorics and geometry, which I'm going to explain today, which we will see next time, and more combinatorics in the third talk, you can kind of take that as a as a reason why we want to study Soergel bimodules. As you probably know, so just let me repeat, there is of course a web page with all the details. I hope you check it from time to time, and if you have done this, then you will see that the seminar itself is divided into 2 parts. The first, I will do some basic algebra, construct Soergel bimodules, not today, but we will construct Soergel bimodules in the first 5 talks, which I call the classical theory. So a little bit about the history. The Soergel bimodules are by now 30 years old, and basically the classical theory is how they were constructed 30 years ago. And the second part will be, I hope, the most exciting part of the seminar. Then I will explain, or we will explain, or we will learn together how actually this fairly elementary construction of Soergel bimodules can be given a diagrammatic interpretation. So it's kind of a blueprint example of diagrammatic calculus, which we will learn together. And in the end, there will be the main theorem. In the end, will be kind of the algebraic construction, which we will see in the first part, and the diagrammatic construction. They are equivalent. So whatever you prefer, I prefer diagrammatics, but whatever you prefer, you can basically choose one of them, and you can play them against each other. So sometimes it's easier to do arguments using algebra. Sometimes it's easier to do arguments using diagrams or combinatorics. And there's a third part of it which we don't discuss, which will be connections to geometry. So you can also play geometry against each other, right? Against diagrammatics and algebra. And yeah, so before I start right into today's talk, so the beginnings, Coxeter groups. Let me just mention one more thing. What do I assume that you know? Well, basically, we want to learn Soergel bimodules together. There will be certain things which you might not understand immediately, but the point will be that everything is amenable to examples. So you should give examples, and basically 80% of my talk will be just examples. And everything, we try to learn everything along examples, as you will see, and these are very important. That also tells you how explicit actually all these constructions are. Okay, so let me start with today's talk. And the name of the talk is, well, the classical theory, part 1. Classical theory part 1, and it will be about Coxter groups. So I called it Coxter groups, the beginnings. And the main goal for today is to understand why Coxeter groups, what they are, and why they're interesting. So Coxeter groups. Okay. Okay, so what are Coxeter groups? Well, the first part of this talk is just devoted to tell you two different, completely equivalent pictures of what Coxeter groups are. One is combinatorial in nature, which I will go right down in a second, and the other is geometric in nature, which I will discuss in about 30 minutes or so. And the point is they're equivalent, so whatever you prefer, again, you can either, some arguments are easier doing some kind of geometric arguments, some arguments are easier doing some purely combinatorial or algebraic arguments. And along the way, we will see the first instance of diagrammatics. Very easy diagrammatics, which you might have seen before. If not, we will see it. But still, there will be already some diagrammatics here. And in the end, that's always keep in mind, that's what I'm trying to say. These Coxeter groups are kind of the combinatorial shadows of Soergel bimodules. Okay. So what is the Coxeter group? Well, the definition is actually pretty easy. So let me start. So there's a little bit of confusion whether people call it a Coxeter group or a Coxeter system. So let me start with the Coxeter system. I take a W and an S, and I call it a Coxeter system. So W and S is a Coxeter system. If the following holds. Okay, so W is a group, and this will be what is called the Coxeter group. Classically, it's denoted by W because these generalized Weil groups. If you don't know what Weil groups are, don't worry. But that's why it's denoted W. So W, throughout this lecture series, will always be a group and then a Coxeter. W is a group. And S is a finite set. This is my alphabet. I want to figure of it as my alphabet. So why do I want to think of it as an alphabet? Well, I will not write down words in this set. Right? So whatever the elements of the set are usually denoted by S1 up to whatever, SR. And I will write down strings, so words in those symbols. So that's the first part. Then I want to fix a certain matrix. So this guy is usually called the Coxeter matrix. We'll see an explicit example in a second. And it has some entries. And ST for ST in my fixed set S. Okay. So my fixed set S. I have a matrix, and it satisfies the following properties. And on the diagonal, you see the entry 1 only. And it's symmetric, so MST equals MTS. And my entries are special. My entries are, so the non-diagonal entries are from the set 2, 3, 4, 5, 6, up to infinity. 3, 4, and so on, including infinity. So I allow the strange entry infinity in my matrix. So if you've never seen this before, here are two examples. For instance, this would be a Coxeter matrix. Whatever. Right, on the diagonal it's 1, and the off-diagonal entries in this case is symmetric, so I can choose one of them. Let me choose 4. Okay, but this could also be a Coxeter matrix. So the symbol infinity is allowed. Okay. So those entries. I'll make it even more combinatorial in a second. So I have those entries. And the point will now be that the group G and the group W is actually, it has a generators and relations presentation. I will explain in a second, or using examples, what that means. It is actually generated by the elements of my set. This just means any element here is a finite word in those symbols. We'll see an explicit example in a second. And, well, those elements, the Coxeter matrix, this tells you the relations. So you have two types of relations. Each generator, and you will see a geometric interpretation of that also in a second. Well, not in a second, but maybe in 30 minutes. Each generator squares to 1. Okay, good. This is called the reflection equation or the quadratic equation. And then a little bit of a funny one. So whenever I have two generators in my group, let me call them S and T, then they satisfy a relation that whenever you have an alternating sequence of them, ST, 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 okay, and so on, of my pre-chosen lengths, ST, then you can turn it around. And it's the same as reading in the other way around. ST, T, S. And that's it. Okay, this guy is called the break relation for a reason we will see in a second. And that's it. That's the definition of a cockster. Looks fairly strange if you see it for the first time, but you will see now, because I'm now going to give examples now, that this actually generalizes a lot of groups that you've seen, well, previously seen in your mathematical life. So everything is about examples. Look at the definition. It will be upstairs. Let's do some examples. Before doing examples, I want to find a nice way to encode the cockster matrix. And the way to encode the cockster matrix, you do it here, is to use a graph. Okay? Cockster matrix corresponds to a graph, corresponds to what is called the cockster graph. And I will explain in a second what this is. What is a cockster graph? Well, the matrix has a certain size, right? It's 2 by 2 upstairs in my example, n by n in general, or what was it, r by r in general, depending on the number of elements in S. So I just draw a graph where my vertices are indexed by S. Okay? So this is a very boring graph. It's a non-connected graph. I just draw one vertex for each element of S. Okay, so far so good. But of course, my matrix has certain issues. And the convention is that I just draw an edge between those two guys, and I label it with a corresponding entry. Okay, I would write my M, S1, S2 up here, and so on. The diagonal is omitted, so I don't care about the diagonal. I will give it more explicit example in a second. So I would write down M SR minus 1 SR on this edge. It's exactly this. If you think about it for a second, it's exactly the same datum as writing down the matrix. So the explicit example you should keep in mind. So let's do the one from upstairs. Okay. In this case, I would write down two vertices, and I would connect them with an edge. One vertex corresponds to the, well, let me call this S, let me call this T. So let's say S is ST. of them is S, one of them is T, and I would write down exactly this element. And I don't care which one because it's symmetric, I would write down exactly this element here. And what is it saying? Well, this is saying that in my group I have the following relation. ST, ST, that's the length, that's the symbol you see here, equals TS, TS. Okay, so let's jump into examples. And the first example, which you always should remember, is that the Coxeter groups generalize the symmetric group. Remember, the symmetric group is just a permutation group of, let's say, the set 1 to n. And the Coxeter groups generalize, vastly generalize these symmetric groups. And this is usually called the type A example. Well, it's just called the type A example, okay? And the point is, the only thing I need to tell you now is what kind of graph I have. The graph will determine everything, okay? I just write down the graph, and from the graph, we will deduce certain like properties. So, usually called type A1 is the following graph. It's just a vertex, and let's call it S1. Okay. Type A2 are two vertices, S1 and S2, and I put an H between them. And here comes a slightly funny convection. So this is basically what a Coxeter graph should be, but a lot of people are lazy, including myself, and in this whole presentation, you usually omit edges labeled 2, you see the second Y, and omit the number 3. That's kind of the classical convention in the setup. That's what you always see. That's also what the book does. It is a bit ad hoc, but I admit it's a bit ad hoc, but this is a convention. So in particular, if I'm writing this graph, and well, here's nothing, right? So it's just a vertex. If I'm writing this graph, then this secretly wants to be this graph, right? Okay, type A3 would be this graph, 3 vertices. So this number refers to the number of vertices. I would put 2 edges, and both of them are labeled 3. And so on. Type AN, I would write n vertices, just a line. So kind of the easiest graph which I can imagine, except the non-connected one, is a line. Right? The easiest graph. That's the blueprint example of Coxeter groups. So let's study this case for a second. I have one generator. W is just one generator, and this generator satisfies, well, the only relation I have. This is vacuous, doesn't exist. And I only have this relation, so it satisfies S1 squared equals 1. Very good. And, well, you have one generator, so you can write down words in one generator. They always look like this, obviously, right? If you have an alphabet with just one letter, well, everything is just a concatenation of those letters. And this relation tells you, let me do one more, that this guy is equivalent to, well, whenever you see two symbols next to each other, you can cross them out. Okay. Right. So you can easily convince yourself that the only thing you can write down is either a string of length 0 or a string of length 1. So this is actually isomorphic to S2, the symmetric group in 2 letters, which is bimodules. And this is so Sn, recall, Sn is a symmetric group of the set 1 to n, which just means all permutation of that set, right? If I can only permute 1 and 2, well, there's not much I can do. So S2 permutations of 1 and 2. What can I do? Well, I can either permute, don't permute, that's identity element, or I can permute them, and that corresponds to this generator. So obviously this group has 2 elements, so does this group, but this group already comes with a nice presentation, and it's a matter of checking that this is actually isomorphic. So let's study this case a little bit further. So now in this case, I would say W, let me call my 2 generators S and T, to not get too messy with the indices. W is generated by S and T in S. Yeah? Oh, let me not write in S. Just generated by S and T. And what are the relations? Well, we always have those relations. And then you have this funny break relation. So the number is 3, so because these 3 symbols. So let's play with this group for a little bit. If you already wonder, this will be isomorphic to S3. Symmetry group with 3 letters. And in general, this guy will be isomorphic to Sn, the symmetric group on 1 to n. So this, before I will play around with this group in a second, but just look at this. I take one graph, a very easy one, a line, and I already have the symmetric groups. So all symmetric groups are encoded in this dictionary here. I mean, I think this is pretty nice. Symmetric groups are kind of the easiest non-trivial groups you meet in your life. And the easiest kind of graph encodes those symmetric groups. Okay, but let me play around with this guy a little bit. Because it will give us the second interpretation of Coxeter groups. Where's my... Okay, so let's play a little bit with, well, I told you, the only thing you need to remember is the graph. I want to play a little bit with this graph, calling my generators S and T. Also, okay, what can I do? Right? I have my group, and each element is a finite word in my symbols in my alphabet S. So what can I do? Well, I can write down nothing. I call this identity. I can write down an empty word. I can write down S, I can write down T, for sure. I can write down ST, or I can write down TS. Still looks pretty good to me. I could write down SS, but remember I have the relation, whenever you see 2 symbols, it's just 1, so you can cross them out. I don't want to write down. Very easy thing to remember, whenever you see 2 neighboring symbols which are equal, you can cross them out. Okay. So I can certainly write down those. Length 3 elements, well, what kind of length 3 elements could I write down? I could write down STS. Again, using this rule, I never write down symbols which are the same. Or I can write down TST. Right? But my relation tells me that they're actually equal. And it's not completely obvious, but this is everything I can write down. So this group has 6 elements. So let me just give you, that's something you need to prove, of course. It's not so hard, but let me just give you a hint why this should be true. Let me write down, let's say this one, ST, ST, S. So what can we do? Should it be on this list? Well, let's look at it. I see 3 symbols lined up. And I know a relation, so I can turn them around. T, S, T. And now 2 symbols next to each other. 2 symbols next to each other. And this actually secretly was already just the word T. Okay. In general, this is very hard. You see a very nice way to determine whether 2 words are equivalent or not later on. But in general, you would write down any string and you wonder what is kind of the shortest expression you can find. In any case, in this case, this is my group. So my group has 6 elements. All right, how many groups with 6 elements do we know? Well, I know 2. I know 2. Nah, well, I know 3 actually. But you can easily convince yourself that this is supposed to be S3. Why? Because those are not equivalent. So it's certainly not a commutative group. Right? Right. So it has to be S3. And let me explain how the projection actually works by removing those. Then you will see how it works in general. Right, let me repeat. We have 6 elements. You would look up the list of groups of order 6. You would find, there are not too many possibilities. It can't be a commutative group. It doesn't look like it wants to be. Those are not equal, right? So it better has to be S3. So let's try to find an isomorphism. And I claim I can write down an isomorphism from this W of type A2. Right, W type A2 to S3 by sending S2 the simple transposition which just swaps 1 and 2. I will draw a picture in a second. Just a transposition which swaps 1 and 2. And I can write down T is a transposition that swaps 2 and 3. And well, let's check. So let me give this a symbol. I want to do some diagrammatics now. I want to think of the symmetric group in, let's say, what is this? S3. So symmetric group in 3 letters, 1, 2, 3. I want to think of them as permutation diagrams. So I want to draw this diagram. So it takes the input 1, 2, 3. It doesn't do anything to 3, right? So 3 stays what it is, and it puts out, spits out 2, 1, 3. So it's a simple transposition that swaps 2 and 3. And that's just by picture for it, all right? This is by picture. Here you can see this, the starting set, and here you can see the permutation. Just by picture. Similarly, I would draw this picture. It doesn't do anything to 1, and it swaps 2 and 3. Okay. So now let's check the relations. Remember, we had this relation, S squared equals 1. Well, let's draw a diagram. What is concatenation? Well, let's just take this diagram and stacking on top of itself. We'll see this in a second. So this one, and you stack it on top of itself. This is a concatenation of 1, 2, and 1, 2. Well, why? Well, let's see. So what does 1, 2, and 1, 2 do? You first swap 1 and 2, and then you swap 1 and 2. So we haven't done anything. And let's see whether we can see this here. Well, I didn't do anything to 3. I follow 1, and oh yes, it ends up where it started. I follow 2, and indeed, it ends up where it started. And my relation says that this is trivial, so I can pull it apart. And this is certainly true in the symmetric group. Right. Similarly for T, just the other 2 entries. And now, let me do the other one. That's a bit harder to see, but not too hard. The other one was STS equals TST. STS equals TST in diagrams S, T, S, right? STS, S is the left one, T is the right one, equals T, S, T. Okay, so let's check. Well, this guy takes one and sends it to here. This guy takes one and it sends it to the same end. So this is great. It's a good start for my proposition to be true. It takes 3 and sends it to here. It takes 3 and sends it to here. And well, there's nothing left for 2. It takes 2, send it to here, send it here. Sorry. So as permutations, they are certainly the same. And the point is that my presentation says, so if you believe my theorem, if you want, that these guys are always symmetric groups, then the point is that those relations, those two relations, this is a great relation. I will draw a nicer picture in a second. That these two relations are completely sufficient to describe symmetric groups. Right? I will always send, in general, I will send S1 to the simple transposition 1, 2. I will send S2 to the simple transposition 2, 3, and so on. I will send S, whatever it is, n minus 1 probably, to the simple transposition n minus 1, n. And the relations they satisfy are precisely the relations of the Coxeter group. Up there. So completely encoded in this very boring graph, or maybe not boring, but very simple graph. This is a pretty nice theorem. This is due to Coxeter. That's why it's called Coxeter. This is a pretty nice theorem if you think about it. Remember that this is really a theorem, so there would be something to prove. But I'm completely hiding all proofs here anyway. I'd rather go with examples. The reason why this is called the break relation is the following. Well, if I think of these strands being arranged in R3, and I would draw them rather like this, like one strand crosses over the other, then this relation actually would look like this. Oh. This is equal to and if you stay on this picture for a second, just do it, then you would see, or you will see, that I have one strand here. Everything is arranged in R3, right? I have one strand here which is completely on the top of the picture. And whatever happens in the background is in the background, right? So if this is now in R3, then you could just pull it down, and this is exactly what this relation says, because this strand is facing you, it's facing towards you, it's in the front. And this is why it's called break relations. So these Coxeter groups actually come directly from some kind of low-dimensional topology. Okay, summarize what I just said. Coxeter groups generalize symmetric groups. That's basically everything I said in the past 15 minutes. And so the bimodules will kind of generalize this picture again. Very nice one. Okay. One more example, kind of opposite kind of example. So Coxeter groups generalize symmetric groups. Coxeter groups also generalize symmetry groups of polyhedra. So let me explain. This is where it comes from. Okay. Give me a second. The board. Okay. Let's take a short break together and let's think the way have I seen symmetric groups, symmetric groups before. Symmetric groups are symmetry groups of certain very nice objects. So the second example are the Hilo groups, kind of the building blocks of Proxima groups. And for some strange reasons, these are usually denoted as type I2N. God knows. I really don't know why. If someone knows them, let me know. So what are these? Remember, maybe you should have seen them before, hopefully. So let's take a geometric object. Let's take an anyone. Let's take a trigon. What is a trigon? Well, oh, this is a bad picture. A trigon is of course just a triangle. It should be regular, so there should be a regular triangle. I can't draw triangles. Let me give it another try. Okay, and what is the symmetry group of this guy? Well, it would be the group of all translations or rotations or whatever you can do to this picture. This is labeled endpoints 1, 2, 3, let's say, such that if you do something and I look away, and you've done something, and I look again, then I can't tell the difference. So it should be everything you can do to a triangle without changing the triangle itself, the appearance of the triangle. And it's pretty easy to see that this actually is the symmetric group in 3 letters. Well, what can you do to a triangle without changing it? You can exactly permute the vertices. If I would permute this vertex and this vertex, and you don't see those labels, then the picture is exactly the same, right? Just mirroring along those axes. It's just exactly the same. More general are the Hilo groups. So let me do the next example. Would be the square. And I wonder what is the symmetry group of the square, right? Well, question. Okay, let's do it. Let's try to do it. Again, these have secretly labeled edges, 1, 2, 3, 4, whatever. But what can I do to a triangle? What can I do to a square without changing it? Well, there are 2 things I can do. I claim there are 2 things I can do. I can take a hyperplane here, so I just cut the square in the middle, and I think of it as I reflect it along this plane. So this operation would change this vertex, these 2 vertices, and these 2 vertices. Of course, the square remains the same. I would say I could also take this one, but this is kind of the wrong thing to do. What you can do here is you can take, so this is my first one, let me give it a symbol. Let me call it S. So let me do it in spin up, or maybe that's bad. Green on a green blackboard is pretty bad. Let me give it a symbol, let me give the color and the symbol, let me call this operation the S operation, and put it in blue. The S operation. The other operation, we do it in red. Okay, I can mirror along this axis. Well, I can do this one. I can again reflect along this axis. Let me call this a T operation. So this operation would fix those 2 points. They lie on my reflection plane. It will swap those. Okay? And it turns out that this is exactly, so those two reflections give a presentation of the symmetry group of the square. Okay, so this guy is actually isomorphic to the following presentation. I have two colors, T and S, and well, let's see what they satisfy. Well, if I do S twice, I take this point to here and this point to here, do it again. Well, reflections, that's why it's called the reflection equation. Well, reflections have the property that whenever you do it twice, you've actually done nothing. That's why it's a reflection. It's a Simon operation. Same here. Very good. So this was the easy one. It already looks good. It already looks like a Coxeter group. Right? This is why it's called the reflection. This is why this is called the reflection equation, as I said. A little bit harder to see. Maybe I will just write it down. And then we track it here on the picture. Is the following. Whenever you do ST, ST, then it's the same as having done the opposite way around, but not before. So let's see whether we can do this on the picture. So let's track this point under STS, whatever. I first do S, so my point goes here. I do T, my point doesn't move at all. Right? It stays here. I do S, my point goes here. I do T, and my point goes here. Okay, same picture. Gets a bit too messy. Okay. Again, I take my point. I do T. Goes to here. S. Goes to here. I do T, it doesn't move. I do S, goes to here. So I land the same spot. This is not quite a proof that they are the same. I would have to track all the other points. But I mean, this is easy to see in this case. Okay, so this is great. I mean, this is a Coxeter group. And actually, which one is it? It's this one. The Coxeter group of dihedral type. So this is called the dihedral group. So those symmetry groups of those regular polytops that we'll do another example in a second are called dihedral groups. This is exactly this Coxeter diagram. There's two vertices, one blue and one red. So already at this stage you can say Coxeter groups generalize groups attached to regular polytops. One more example, and then one more example to convince you that this is really true. But of course, you wouldn't need to prove everything. Okay. One more example. Now it gets tricky. Now I'm attempting to draw the next regular polytope, which is a Pentagon, and of course it never works out. Pentagons are very hard to draw. I will try anyway. Let me try to draw a Pentagon. Oh yeah, this doesn't work. Okay. Kind of. Kind of Pentagon. Where is my no? Red and there's blue. Blue is good. Again, I claim I can realize this is a cockster group. Again, I want to know the symmetry group of this guy. And I would take a reflection here, let me call it S. And the first operation is to reflect on this axis, so it would fix this point and would change those two, for example. And another one, another one goes to the next angle here, so this one. It's a really bad picture, but I hope you get the point. This is D. This is a really bad picture. So this would be a legal reflection. So it would exchange those 2 points. Just my picture is extremely bad. In any case, you can check that this is actually equal to our Coxeter group is T. Well, they're reflections, so S squared equals 1. And the crucial thing would be the break kind of relations. I don't want to do it live now because I would mess it up and I'm also running bad on time. But you can check in this case that you have it's a 5 gun and you relate 5 relation. That's not a coincidence. That's it. So it's a Coxeter group of the following type. 5, red, and blue. And I think I swapped colors. Yeah, it was blue and red before. Forgive me. And the general statement is that the Coxeter group of this type, this is I2N, and the N is exactly this label, and the 2 is just the number of vertices. The Coxeter group for this one, so it's W of I2N, is isomorphic to the dihedral group. Again, there is no constants of rotation, let me just call it D2N, whatever it is, and this is actually the symmetry group of the regular angle. The idea is the same. You write down your regular angle, you pick one reflecting hyperplane, turn it by the corresponding angle, you get the next another reflecting hyperplane. Those two are your reflection generators, and they will satisfy exactly this relation. And this is a not completely trivial theorem due to Coxeter himself. Okay, so summary of what I just said now is Coxeter groups also generalize, not quite, but let me summarize nevertheless. Coxeter groups also generalize symmetry groups of polytops. Why not quite? Well, let me just give you one more example. So the symmetry groups of all platonic solids will turn up as Coxeter groups. The only platonic solid I can draw is the following. So the symmetry group of the, well, maybe I can draw another one, but anyway, I can draw the symmetry group of Q. Well, kind of a cube. It has the following axes. It has some hyperplane cutting here. And you would reflect in this hyperplane, let me call it the S hyperplane. You would have a hyperplane going like this. So through the diagonal, we call this a T hyperplane, and you reflect through the diagonal. And you have a hyperplane going like this. Where are we? Whatever. Let me do it purple. Let me call this U hyperplane. I know this picture is very bad. Basically, what you do is you cut your square in a correct way into hyperplanes, and this is actually isomorphic to the group generated by S, T, U, subject to the quadratic relations. Well, let me write it down in terms of Coxeter diagram. So this is actually the Coxeter group of this diagram. So you vertices, right, S, T, and U. And well, if you're not like me, you could draw three-dimensional pictures a little bit nicer. Then you could check that these satisfy a three-term relation, these two commute, and these two satisfy a four-term relation. Anyway, the point is, Coxeter groups, okay, have this very easy presentation. Just writing down words and performing certain operations, right relations and quadratic relations, but they actually generalize a huge bunch of nice groups. Let me just mention that they also generalize Weyl groups, if you know what a Weyl group is, but that's why they call it W. But this is kind of the geometric picture. They're kind of a mixture between the symmetric group and the symmetry group of certain regular bimodules. Very good. Oh, this doesn't work. And now comes the main theorem about Coxeter groups. So the basic question would be, so what on earth can we do? I mean, combinatorially they are very easy, but in general, if you would write down two words in your alphabet, imagine you have a huge graph with crazy edges, how can you actually tell whether they are the same or not? I mean, in my baby example, which is not on the board anymore, where I wrote down one S, T, S, T, T, S, and so on, it was not so hard. But how to do this in general? Right? So the question I want to ask for the remainder of the time is okay, these are very nice groups. Maybe it makes sense to study them further. So how can we tell? Right, it's a combinatorial object. Combinatorial objects have the nice advantage that they're usually very easy to write down. They're easy to explain. You can sit down and do calculations. But sometimes they're a bit tricky. So for instance, how can you tell, just combinatorially, whether two words are the same? Two words in my Coxeter system are the same. For general group, you can ask the same question. This is known as the word problem. It's actually a name for the word problem. In general, this is impossible to solve. Take a general group, some combinatorial definition of it, some general relations, no chance. Here you have a nice answer. This is called the word problem. Okay. Okay, so I'm basically asking if I have a word in S, let me call it W underline. Right? W is my element of the group. W underline is a specific word representing it. And I have another word, W underline prime. And they're both presenting some W prime, and I want to ask, let's say they're both representing W. So how can I tell? Well, they should be the same, but how can I tell, right? How can I tell? And here comes the answer. It's a really beautiful answer. It takes me a while to get there. But the main idea is to use what we have just seen. This presentation, this geometric presentation. The answer is due to Tietz. I will write it out explicitly. Theorem. I will explain it very explicitly. I will construct it, and then we're basically done. Tietz theorem says the following: the word problem is solvable. In other words, for each WS, so for each Coxeter group, there exists a finite dimensional FD real vector space. And you will see where the real numbers come up in a second. Real vector space. Let me call it V, whatever, such that let me just write the abstract nonsense and then I explain what is actually happening. Such that W acts faithfully on V. Acts on V faithfully. Okay. What does this mean? Right? Okay. Groups can act on vector spaces. Groups can act on sets or on vector spaces. So far, so good. What does faithfully mean? Faithfully means just the following. If I take these two words together, finite dimensional and faithfully, then this means the following. Those will imply that, well, I would assign to each word, I would assign a matrix, a real matrix, right? So this has some dimension, let's say 5 dimension 8, let's say this is dimension 8, whatever, a real n by n matrix. To each word, also to my W prime, I would assign a real n by n matrix. Let me just give it some name. Whatever, f of W underline, f of W underline prime. So I want to say this actually is called f. And this faithfully, so this now means the following. It's really amazing. It says, faithfully says, okay, f of W underline equals f of W underline prime if and only if W equals W prime. In other words, you want to check whether two words are the same. Use this construction. You get two matrices. The only thing you need to check is whether the two matrices are the same. And that's easy. You just look at the matrix. Right? On the nose the same. There's nothing involved anymore. You just send it to a matrix and you check whether this is the same. Okay. So this is already pretty amazing. Right? You have a combinatorial given object, which you like to understand because it generalizes something. You can argue, well, let's just say something very nice. And you basically can't do anything, but then Tietz comes around and says, oh yeah, you only have to check certain matrices, whether they are, and you can basically solve all problems in your Coxeter group by doing some linear algebra with those matrices. And really here's the two words, finite dimensional and faithfully are important. So finite dimensional tells you that it's really a matrix that you have to check. And faithfully is this condition. It tells you, well, the only thing you need to compare are matrix entries. However, this theorem, as amazing as it is even more amazing because this representation, I will write it down in a second, so this is called a representation, this action is completely explicit. So you give me a word, you give me a W underline, and I give you a matrix. That's how explicit it is. Or you give me a word, I fit it into a machine, and the machine gives me a matrix. So this is computer understandable language. Let me explain how that works. Just need another board. And then I have something like 15 minutes to wrap up. And if you're still not convinced that Coxeter groups are nice, next time you see another geometric interpretation of Coxeter groups, they're really geometric objects. And Soergel bimodules will generalize all of this in a diagrammatic framework, which is extremely amazing. Okay. So this action, which is still upstairs, it's usually called Tietz geometric representation or Tietz reflection representation, or just geometric representation or just reflection representation. If you don't want to be so picky about giving credits. Okay. Let me construct it for you explicitly. The only thing I need, I will start with a vector space. Okay, so that's V, a real, let's say n-dimensional vector space. Good. And I want to think of it having a certain basis, which I call, so this is the span of elements, which I call alpha 1 or alpha s for s in my given set S. Right? There's one basis vector for each node of my graph. Okay. And well, I want to define a certain pairing on it. I need to cheat because I always get my signs wrong. I want to define a pairing, a bilinear form, which is not quite the standard one. So you shouldn't think of these as being standard vectors in Rn. This is of course isomorphic to Rn, but that's kind of not the point I want to take. Because I kind of want to use a certain bilinear form which kind of measures angles between those vectors. I will draw an explicit example in a second, of course. And I would say just the following. So alpha s, alpha t, they pair as follows. There's a minus, but the minus I always get wrong. And now comes the point where I need real, and now comes the point where I should see angles. I take the cosine, we'll draw a picture in a second, of, well, some angles, relation phi, yes. And, well, remember, I have my Coxeter graph here as t. So locally, my Coxeter graph is like this, and here's an MST. Right. What does this mean, actually? Well, we have seen this before. Let me do an example for you. Let me do the example for exactly this diagram. Okay. In this case, I would need a two-dimensional real vector space. I have one. I call it the blackboard. Here's my two-dimensional real vector space. Oh, by the way, this means actually that they are normalized. Because, well, cosine of pi over 1 is 1. Okay, so this is an orthonormal basis. My picture will be horrible, of course. But let's see. So I probably won't make it. Probably the lengths will be different, but you get the point. So here's my real vector space, two-dimensional. I call it the black rock, as I said. But I don't want to take the usual vectors. I want to take vectors which have a certain angle in between them. And if you if you believe me, then the cosine of pi over 4 is one of the nice angles. That's the one that corresponds to 45 degrees. It's something like 1 over square root of 2, I think, or something like that. Anyway, it corresponds to 45 degrees, so I would write down two vectors in my vector space. They should be of the same length, but let's not worry too much about that. Good. So let me call this alpha t, call this alpha s. Okay, and this is the condition that they have a certain angle here. This is this cosine pi over 4 thingy. Okay, so far so good. That's kind of the data which I have so far. And now I claim something we would need to check, but I will make this in a second. So what Tietz actually did is Tietz says now the following. Well, my generator S of my Coxeter group can act by the following operation. So I want now an endomorphism. So from W to end of my V, and I would send the generator S to, well, the matrix, the endomorphism of my vector space, given by reflecting, actually, well, this is probably T and S, to be consistent with what I did before, by reflecting corresponding to the hyperplane spent by S. The formula will look like this. Give me a second. So of course you span a plane, right? It's a hyperplane. And you would reflect in the hyperplane orthogonal to that. In this case it's a bit boring, but it will reflect in the hyperplane orthogonal to that. So here's the S hyperplane. Why do I want orthogonal? Well, you should think of this as happening in dimension 506. And this is just a vector. I can't reflect in a vector in dimension 506, but there is an orthogonal hyperplane, and this is, or it's really a hyperspace. It's codimension 1. It's 1 dimension lower. In this case, it's also a line, and I can reflect in this. So let me call this the alpha S hyperplane. Similarly, something like here. Alpha t hyperplane, and well, I send it to reflection in the corresponding hyperplane, basically. And in coordinates, it looks like this. It's a matrix, so I take something in my vector space. Let me call it lambda. And if lambda is mapped to the following expression, lambda, this is just a geometric, is a coordinate interpretation of what I just told you, that I can never remember it, so let me just do it. Minus 2 times, and then now I take the angle. Okay. And Tietz says that this is, Tietz theorem says that this is a faithful representation. So exactly as before. This is really explicit. Let me make it in coordinates in this picture to convince you that this is really explicit. hopefully this example will say that those cockster groups are actually not scary at all. They have nice geometry, they have nice algebra, they behave nicely. You can do everything with those. There are whole computer programs doing computations with cockster groups, mostly using, well, representing them by T's theorem. Okay, let me come back to this example upstairs. Here we go. Do it explicitly. So I have, well, I have S and I have T. And how does S, the matrix, this is assigned to, let me call it again, F, to a matrix SF, Fs, and this is assigned to a matrix Ft. And these, of course, 2 by 2 matrices by construction. And I only need to tell you what they do on the corresponding basis elements. And this is how it works. Okay. So let me think of having alpha S, alpha T here. Alpha S, alpha T. So the image of alpha S goes here, the image of alpha T goes here under this operation. So let's see. This operation says that alpha S goes to alpha S minus 2 times the pairing, which I told you is 1. Well, we can check it. It's this cosine number, it's 1. So this is just minus alpha S. Okay, so I put a minus 1 here, and I don't see an alpha T, so I put a 0 here. Okay. Alpha T goes to, using the same formula, no? So we only, okay, this is alpha T, and there's some multiple of alpha S. So you certainly get alpha T, and some multiple of alpha S. And what is this multiple? Well, this is minus 2 times minus cosine pi over 4. Well, this isn't as complicated as it looks like. It's actually pretty easy. This is minus and minus, I don't care. So it is 2 times cosine pi over 4. And this is, well, believe me, or use your iPhone to do it, whatever. This is square root of 2, so this is just square root of 2. I mean, this was just a calculation. So this is square root of 2. Right? I need real numbers. Here's the square root of 2. You can also check that this one goes to the same calculation. Minus 1 here, you get the square root of 2 here. And you get a 1 here. Right, 2 explicit matrices. And now you wonder, well, ST equals TS question mark. What you do is you just multiply those matrices. I'm not going to do that live. If you want, of course, you can multiply 2 by 2 matrices. And you will check actually that those are really equal. So on this side, you will get exactly the same as on this side. And if I'm not completely mistaken, then there should be the action of the longest element or something like this. Okay. So instead of answering this question, well, combinatorially, I can just look at the matrix and, well, there you go. In practice, of course, you would just have some computer algebra system, you just write down a word, just write down another word, and the computer secretly does exactly this and tells you, oh yeah, they are the same or they're not the same. Right? Remember that this is an if and only if. So I could write down now STS, and I could ask, is this actually equal to T? Well, T is easy, I would feed into the corresponding calculation, and I hope I will see that the answer will be no by looking at the matrices. Okay? Just by looking at the matrices. Say it again because it's important. Coxeter groups are a matter of computer algebra. This is what Tit theorem says. Okay. Okay. While I'm cleaning the board to write down a few things we need for later, don't worry. So it won't be too bad. But let me just summarize what we have seen while cleaning the board. We have this notion of Coxeter groups, of which you should think of as being a shadow of a richer structure called Soergel bimodules, which we will see in this seminar. And they come from geometry and from the symmetry group. They generalize the symmetry group and like nice pictures in geometry. They're pretty handleable. They're pretty easy to understand in the sense that, well, you can feed Tit's theorem, I said again, it's just saying you can feed any problem you want about Coxeter groups, you can feed it into a machine. That's what Tit's theorem is actually saying. Or if you're very brave, you can do it by hand, but I can't even do it by the way. Okay, so this is really easy to understand the groups, and we will see in the next two lectures that this is not even everything. You can say so much more about these Coxeter groups. It's really amazing. Very basic, very simple objects, and you can say so much about them. It's pretty amazing. Okay, this was the summary, and well, now I can play a little bit more with your Coxeter groups, and you will do the following. You need the following combinatorial notions. Let's go back to combinatorics. So let me just take one W in my W, and of course now let's say from now on I fix the Coxeter system. I take W in W, and W has many expressions, right? We've already seen this. There's W underlined, there's W underlined prime, or whatever. W twice prime. But kind of they are nicer expressions than the general expression. Just think of this example. I could write down S as it is. Remember, it was this example. Okay, S as it is, or I can do the following. A very strange expression. Let's see whether I've got it correct. And I apply a direct relation here. I cancel those two. I cancel those two. And I just decide, yeah, okay. Let me write the TS here. Okay. So here's another expression of TS. Certainly this one is preferable. This is just long. This is nicer. And you just call the length L of W. Just the minimum over all expressions, so the minimal length over all expressions. But the length here would be 2. And how could you check that the length is 2? I mean, that might be a shorter expression. Well, we can use Tit's theorem. You could check that everything, well, everything that is shorter would be ST or 1. All of them have different matrices, so this is a reduced expression. And what is a reduced expression? Well, W underline is reduced, is a reduced expression. Well, and I call this a Rex reduced expression. Rex. If, well, what could it be? Well, if it can't get any shorter, right? If the length of the word, which is just the number of symbols, equals the length of the one that is represented. So this is reduced. This is obvious, well, not obviously, but it's not reduced. This, of course, has length 6, and this is length 2, and the length of the corresponding element in the group is also 2. Okay, and these are really important in this Coxeter combinatorics. So let me write down the following lemma. Right, so length, it's a numeric value, a numeric invariant to get assigned to your element, and you can check it if you want using the geometric representation. So the lemma I want to write down is the following. So the length satisfies certain properties. You don't need to remember them. But one of them is important. One of them is really important to remember. It will be the last one. But let's just do a very easy one. What is the minimal length you can imagine? Well, the minimal length I can imagine is this one. Sorry, is this one. So the empty word certainly has length 0. And this happens if and only if W is actually true. And similarly, length from W equals 1 if and only if W is in S. Those are the easy cases, and then it gets a little bit messy if you have bigger lengths. Basically, by definition, you will see that the length is invariant under taking inverses. A little bit harder to see, not much harder, is this funny property. The length of a composition is actually smaller than the length of the sums. It's really smaller, right? So this can be much smaller than the sum of the two. And it's bigger or equal to the difference. Either way. Right, you don't need to remember those, but now comes the main point, which gives you an inductive way to think about Coxeter groups. Along the way, but the main property, maybe that is. Is the following. The length of W times S. So S is in S, W is anything. It's almost equal, it's of course not equal, it's the length of W plus minus 1. So it either goes up or it goes down. Up or down. Multiplying with a generator will get the length up or down. So this is the main property. And these are also called up and down, right? Plus is up, minus is down. Right? And this lets me to define and I really want to end with the corresponding theorem. That was really nice. Extremely surprising if you think about it. But for this, I need one more notion. You forgive me. Okay, now there is the length. And the main property of the length, believe me, is the one in orange. And if it only gets up or down, maybe it makes sense to kind of keep track for a fixed W, whether it goes up or down if I multiply with a generator from S. And that's exactly the notion of a descent set. So there's also descent means going down. There's obviously the other notion going up, but I don't need that. So let me just do the descent set. And they come in two flavors, the right and the left descent. They're exactly the same, just right and left. So let me do the right one. Right descent of W is left descent of W is the set of all S, right? Descent, the set of all S, which makes it shorter by multiplying from the right. Such that length of WS multiplied from the right is shorter than length of W. Right? It's a descent. Exactly the same condition. So by using the other properties, you will see that this is not an asymmetric. The main property is not asymmetric. You can do it from the other side as well. Let me give you an example. And then I'm almost done. Of course, the only example I know. This one. Okay, I have unit. I have S. I have T. And I can pick anything for this one, right? It was just the same. And you will see the following. So the right descent of this one, it can't get any shorter, right? So it's 80. The left descent is the same. It just can't get any shorter. It's the shortest term. This, for instance, gets shorter if you multiply it by S, but not if you multiply it by T. If you multiply it by T, you go here. Right? And this one is a funny one. You can check actually here, it's not so hard, that this gets shorter for every T. Whatever you multiply it with, it gets shorter. No matter from which side. This is really asymmetric, so this has right descent T. If I multiply T from here, it gets shorter. The left descent would be S. If I multiply S from here, it gets shorter. Right. And this is a funny property because this is just S. And this is what I call the longest element. So usually we go to W0. And the main theorem I want to end is a classification of those guys. And they play an important role due to the following theorem. It classifies finite Coxeter groups in terms of the descent, in terms of the longest words, and in terms of graphs. Let me write it down. Which is, I mean, classifying finite groups is basically hopeless. Some people have done it. It's a 10,000 page proof, whatever. Classifying finite Coxeter groups is much easier. It's actually due to Coxeter himself. So this is 100 years ago. It's not so hard. You can do it yourself if you want. It's not easy. I wouldn't say you can do it easily, but it's also not so hard if you know the answer to the Coxeter. It's a really beautiful answer. if you have seen these kind of things before. Again, a hint why cockster groups are so nice. If you ask a nice question, what are the finite cockster groups, and you get a nice answer, then it's usually saying you're on the right track. Main theorem, or actually Tietz theorem is the main theorem for today, but really beautiful theorem. Let me call it beautiful theorem. And this is really due to Coxeter. Maybe Tietz. Very natural question. You have something given by generated relations, some combinatorial object, you like it, you know that it connects to geometry, you have done 100 computations, and you ask the question, when is this actually a finite group, right? So, WS is a finite Coxeter system, meaning W is finite. If and only if. First thing is there exists along this word it should be longest, so it's strictly longer than all others. So W is of course not W0. Okay. Exists a unique one. There exists. Okay, you can make everything here with exists, and then you can check that it's actually unique. But let me just phrase it in terms of there exists uniquely an element in my W, which gets shorter no matter what you multiply to it, with right descent W equals left descent W equals S, as in the example above. These are combinatorial properties, so very nice. The Tietz pairing this was this one, the one with the cosines. It's positive definite, so it's a positive pairing. This is a linear algebra interpretation of what it means to be finite. You have a matrix, you check whether it's positive definite, right? The pairing matrix, give you an example, the pairing matrix for this type will be this one. And you can check if this is positive definite. It's a 2 by 2 matrix, you can do that. So this is combinatorics, this is linear algebra, and then there's a really nice one. The Coxeter graph has a certain shape, and I will write down the shapes in a second. Has a certain shape. So we'll write down in a second. Okay, before writing down the shapes, you have an interpretation in combinatorics. You have an interpretation in linear algebra. It's a positive definite. It's exactly what you would ask about such a form. Is it positive definite or not? And if it is, it's finite. Really nice. And kind of the easiest graphs you can imagine will be the ones with the finite Coxeter group. And the easiest graphs are the following. So they come in certain types. The Symmetry Group is type A. Then a version of the Symmetry Group which is called type B. Then another version of the Symmetric Group. So these are permutations, the sign permutations, and these are the double sign permutations. Type D. These are the infinite. There's an infinite list of them. I will write down the graphs in a second. And if you're wondering whether I count A, B, D, which is really bad counting, because why would I don't know? Because Lie theory was before, and in Lie theory there's a type C, but here it's the same. Anyway, so it's an A, B, C, D counting secretly. The type A graph is the following. It's exactly what we have seen. It's a line. And it exists for any number of vertices. Here's the one of, with 4 vertices. The type B one looks exactly the same. It's a line. But one of the vertices has a slightly different label, just label 4. The type B one is a line, as you can imagine, almost a line, and at one end it splits. But that's it. So the only thing it kind of generalizes give you finite things are kind of lines, if you want. This is secretly a line, right? Just imagine that this is, as long as you want, then it's a secretly a line. Just okay, it splits, but who cares? A, B, C, D. Well, then there are some. So these are infinitely many. For each number of vertices, you have the corresponding line. And then you have these funny exceptions. You have the type E ones. Right? And by the way, before I write down type E, this is how a classification should look like. This is a classification of finite cockster diagrams. You should have some infinite families and some finite number of exceptions. This is really a good classification. So type E, you only have 3 by some miracle. It's basically a line, but you have some edge which doesn't want to stand in line. Okay, there's 3 of them. Just write them down. There's another one. They call it E6, E7, E8, just counting the number of vertices. Which is a bit surprising. Right? It looks like a line and then it splits at the end, but this is where it stops. The next one is already infinite. It's kind of these weird miracles. You do need more space. So don't worry, the list is very finite, I'm almost done. A, B, C, D, E, F. And F is the miracle whatever. It's just one diagram. It only exists with 4 vertices. Looks like this. And this guy, as a funny side story, is actually the symmetry group of a 4-dimensional analog of the dodecahedron. And it only exists in dimension 4. A very strange polytops that exists in dimension 4. What is the next one? A, B, C, D, E, F, type G. Also just one. This one, so the symmetry group of the hexagon, which we will see next time. The hexagon plays a certain role among regular polytops. And there's type. There's just one missing. Oh, whatever. Type. Whatever. What is the last one? Type H. Again, some miracle happens. You have something that looks like this. It's again one of these strange regular polytops. Oh, sorry. this is the three-dimensional analog of the dodecahedron. This is a polytope that only turns up in dimension 4. And then there's the dodecahedron type. You don't need to remember this list, but the point is it ends here. Okay? So it's really a good specification. Okay. There are also infinitely many, but kind of they stay at the same thing. So, how I would like you to think about it is that if you want to think about finite, a nice question like when is something finite, you end up with, well, most natural candidates you would write down basically. Line graphs, there are infinitely many of them. Okay, and then you have some low number fluctuations here, like the finite types. But yeah, they're a bit random. That's just what they are. They're a bit random. But in the end, they still correspond to some, like this one. This is called the 24 cell. And the Coxeter group is the symmetry group of this 24 cell. And this 24 cell is a 4-dimensional analog of a platonic solid which only exists in dimension 4. Okay, thank you very much. That's it for today. Let me summarize. And let me say that we meet next week. So let me summarize what we've learned today. Is I gave you the kind of a little bit of motivation why Soergel bimodules should be interesting, because it should generalize this picture. And this picture should be a shadow of a richer structure called Soergel bimodules, which themselves are still easy. That's what we will see. Reasonably easy, of course. They are kind of a mixture between being easy and accessible. Being accessible and have a rich internal structure. Kind of a nice mixture between the two. They generalize this nice cockster combinatorics. The cockster geometry given by reflecting or given by symmetry groups of certain polyhedron, 24 cell, for instance. And cockster groups have very nice answers to very natural questions, like the word problem has a nice answer, it's amenable to linear algebra. Some question like when is it finite has a nice answer. Next time we will see another nice answer. There will be, you can ask the question, how do cockster groups compare to tillings of planes, for instance? So some like tillings geometry, you can already imagine that the sixth-gun, the only thing I can draw will play a nice role here, because with the sixth-gun you can actually tile the planes. Right, I can go on forever with honeycomb things, and you will get tiling of the plane. The 5-gun doesn't. The 7-gun also doesn't, but the 6-gun does. That's why this guy plays a special role. That's what we see next time. More combinatorics of Coxeter. And as usual, I will send around the link on Sunday. And I made a video of this talk, so the video will be made available on my website. As soon as it's converted, it usually takes a while. But if you want to rewatch it, whatever. One last comment, and then we are done. If you don't have access to the book, the book is still paywall hidden, but I have. I turn off the video for a second.